So let's see. First, just so Simon already explained this thing with the Chern character, right? But just those who just happen not to enjoy Simone's exercise session this morning, just I repeat this for 1 second, is that in fact, so there was a problem that was possible but difficult to solve in the problem set. It's about the Chern class of the tangent bundle, which is a bit more difficult than calculating the Chern character. So this is going back to what I was doing last time, is thinking about this Chern calculus as calculus of symmetric polynomials. So so this Chern calculus and symmetric polynomials. And of course, the point is that there are many, many different symmetric polynomials. So there are many bases of symmetric polynomials, and so this is a whole separate subject. You know, the book, in fact, if you want to see what it's about, then you can look at the book of MacDonald, which is the Bible of symmetric polynomials. So we're just touching on this for now. I'll talk about this today, maybe next time a bit more, because this is really crucial for enumerative geometry. But for now, so in a certain sense, of course, we know that this thing is fully sufficient. So if we have a variety and we have a bundle on this, then we defined what the Chern class is, and this was just the product of so this is just the sum of CI V, where this is the ith Chern class, and then this goes, if this was rank R, then this will go from, well, I equals, well, C0 we define to be 1. R, and in terms of the splitting principle, which is with the base, so this is how symmetric polynomials come in, that the splitting principle writes down every Chern characteristic class as a symmetric polynomial. And so each characteristic class is a particular symmetric polynomial. So we can write it this way, where I'll just denote these Chern roots by I. And so then this had the enjoyable property, where this is quite obvious from this, is that, well, using the splitting principle, was that if you have, say, an exact sequence of vector bundles, so you have some W, V, U, some exact sequence of vector bundles, then clearly, because, well, if it's a direct sum, then clearly, if it's not a direct sum, this exact sequence, then it's a little more complicated. But anyway, the splitting principle says that this is always true, that the total Chern class of W is equal to the total Chern class of U and V, the product of the two. Okay, and so this just has to do with the fact that it's just because CV is a product, and so then, of course, this will be continue to be true in this setup. Okay, so this was our formula. The problem is that the Chern class of a tensor product is much more complicated. Okay, so just going back one, well, anyway, in fact, no, I'm not going to go back. So I just want to explain now what this Chern character is, which was just explained, but I'm just repeating it. Is the following. So there is another way of doing this. This is has a slightly unpleasant feature, but it has a lot of very pleasant features as well. And this is the Chern character of a vector bundle. Right? And so this is just this. You take Chern character of the vector bundle, and now I just need to give you another symmetric polynomial. Of course, this, I say it's a symmetric polynomial, but we really think of this as a generating function of homogeneous symmetric polynomials. And so this is the way we'll think of this as well. So this is just going to be the sum of the exponential of x to the I. So it's an infinite series. So, I mean, if you want to write down in this form, so this was just the generating function of the ith. These are elementary symmetric polynomials. So there's as I said, there is a dictionary, symmetric polynomials and character, and these what's called characteristic class or generalized Chern classes are in one-to-one correspondence. For each symmetric polynomial, there is a generalized Chern class. So our usual symmetric Chern classes Ci correspond to the ith elementary symmetric polynomials. And so what are these? So let's write these out. So this is just sum of, so what is, let's write it down in this form now. So this is now this form in the xi form, and I write it down in a slightly different form. So this is the sum of 1 over n factorial of the sum of xi to the n, right? So n goes from 0 to infinity. So it's again a generating function, just like here. Here was the elementary symmetric polynomials. Here is these polynomials which are called power sum symmetric polynomials, and they form another. They help forming another different basis from these ones. So these are perfectly acceptable. These are sometimes denoted by Pn of x1, x. No, x, so I made a mistake. No, I didn't. xr. So this is now sum from here, from I going from 1 to r. There are x's. And here also, this goes, I goes from 1 to r. So this is an infinite set, xr. It's called power sum symmetric polynomials. Okay, so each have their own positive and negative properties. So clearly there's a way to go between them. So there's if I know the power sum symmetric polynomial, so maybe sometimes actually this is the notation in the symmetric polynomial community. You can otherwise in the Chern class community you just write Chern V as just sum of CH. So now I'm just writing this formula, just a formal thing. And so no matter what formula writes down, there is a dictionary between the two. So CHN can be expressed as some polynomial p tilde. So CHN is just a symmetric polynomial, this power sum polynomial divided by n factorial. We can represent it as some polynomial p tilde in C1, etc., CR. So that is polynomial p tilde is a way to express them. That's an exercise to see. Well, the simplest relation, of course, is the very first one. So C1 is just the sum of the xi, and CH1 is also actually the sum of the xi. So actually it's true that, so the very first one is really easy. The next one will be a bit more difficult. Then you need to express what do you need to express? You need to express sum of xi over sum of xi squared over 2, right? You need to express this in terms of those ones. So that would be, how can you get this? Well, you just take the, I guess, C1, which is the sum of xi. So this, yes. So C1 squared, yes. So I just wanted to put this here. Yes, so say x squared, I guess, over 2. And then you need to subtract C2 or something like that, I presume, right? Okay, and then there are polynomials in general. Okay, so why did I tell you all this? There's several reasons, but the main one is that now this tensor product story becomes much easier. So this actually has a perfect algebraic properties the following setup. So first of all, in this case, in this case, you have, so now properties. In this case, you have a similar thing, but a nicer one, an additive one. So here, sort of an additive thing, a direct sum, so you can think of this as a direct sum for this purposes, went into a product of two things. Well, now it's much better. I mean, here you just have that, well, and this is obvious, right? So, because this is just a sum of these things, and when you take the products, this is what you get. So this follows from the splitting principle very easily. But what is wonderful is that now the second question also has an answer. So if you have a tensor product, then now it's a plus. Okay. Thank you. And then the second one is, so now here it's a product. Okay. Okay, so you can do both tensor products now and direct sums, which you were not be able to do here, so it was much more difficult. Okay, and so in fact, this is what you need. If you want relatively easy formulas for the tangent bundle, say, of a Grassmannian, then of course you need you can only express them easily in this form, because they involve a tensor product, and that's what Simon explained. And right, so the Chern character of the tangent bundle, say, of a Grassmannian, will be just the Chern character. So we use our geometric formula. So this is just Hom SQ in the universal sequence, and then this is just Hom Chern character of Hom S. No, that's what I wanted to do. S star Q. So this is just Hom S dual times multiplied by Chern character of Q. Right, and so now we use, of course, our sequence. What is this S and Q? Remember, this is just the trivial bundle C, say, N. So if it's then, so we have an exact sequence here, and so this gives us a relation that says that the S plus equals to the Chern character of Cn, and for Cn all of these things are equal to 0, so the actual Chern character is equal to n. So the trivial bundle has Chern character n, and then this allows you then to calculate those things, because now you can express the Chern character Q through this, and you get a formula for the Chern character of the Grassmannian. Okay. So anyway, so this is the form that's calculable. The other one is a little more difficult. So now going back to our calculations. So where were we? So the idea was the following. We were trying to. The subject was enumerative geometry of sort of now subvarieties of varieties. So we take a smooth variety S, and of course, well, we don't want very complicated things. I want to count the lines, say. So, for example, number of. So I'll think of this as being in Pn, and then we are trying to calculate the number of lines. So in X. So this was thing, of course, well, yeah. So this is the subject I introduced last time, and we did some preliminary calculations. So just I remind you what we did. So the problem is this is actually infinitely, it seems infinitely complicated, and there was a genius trick that makes it actually still dual, and this was this universal Fano scheme. So this set we denoted, so just remind me the notation. So the idea is that if I have this subvariety X in Pn, and so I take so the number, and so number of k-planes. Yeah, so if we use the notation fkx, which is just the variety, well, at this point, just a set of k-planes in X, and here I mean projective k-planes, and I would actually be forced to probably do what I actually hate this notation, but to use the, so in the text there's a dual notation for the, this really becomes very, for just the set of k-planes, right? So we know that if I talk about projective k-planes in Pn, so projective k-planes in Pn, so not in X but in Pn, of course correspond to actual linear k-planes in an affine space, but there the dimension is shifted. So this is just the same thing. So we're gonna, this is this notation I haven't used so far. So the notation is G, K, N, okay? But this of course, in our whole notation, just K plus 1 and plus 1. So it's, you take the projective line in Pn is the same as a two-plane corresponds to two-plane in affine space. Okay, so sometimes I'll use this one, it's just simply, otherwise I need to make these shifts all the time. I more or less I'll identify these two spaces. Okay, so we are trying to describe this fkx thing, and so the genius trick was the following, that this could be very, very difficult, but we have we can construct a global object. So global object is the following. So suppose now we don't look at arbitrary subvarieties, we look at say hypersurfaces. So let's consider X is a, say, degree D hypersurface. And then we can just look at the space of all degree hypersurfaces. Okay, so so we can just look at so what is a hypersurface? So we just look F is a degree D polynomial, and then we have this XF, which is just the zero set of F. And then we can, so this means, and this is this lucky part that you need to remember, because this will be now difficult in a varieties of codimension higher than 1. So it's just the codimension 1 situations, which is easy. This is the situation where you have, where it's easy to describe all the hypersurfaces. So this is very simple. You simply look at the hypersurface, the same as the set of F's. So really the set of hypersurfaces, surfaces of degree D, was just this projective space of all polynomials of degree D. So I denote this by capital N, and this capital N is just the set of polynomials of degree D in N space. So in N plus 1 variables, so that's going to be just N plus D, choose D. This is the set, so the dimension of polynomials over degree D, but not in N, but N plus 1 variables, right? Because it's Pn, so we have N plus 1, that's why you don't see that 1 that's usually there. And I projectivize, so I actually have to subtract 1, so that's the correct formula. And okay, and so then this trick that I'm talking about, the following, that we constructed this general incidence variety. So here I can put G now Kn, So the dimension of this, right, is, so the Grassmannian has a better formula, of course. So this is just k plus 1 now times n minus k, right? Because it's k plus 1 Grassmannian and n plus 1 space, and the usual formula for the Grassmannian is that you take k plus 1, this number, times the difference of these two numbers.
Grassmannian should be like projected.
So I should put this line here. Sorry, so yeah, in principle there's no R in this thing. That's a notation remover. So sorry. There's no R, but I put an extra bar. But of course, by my handwriting you cannot tell if there's an R or there's no R. Okay. So we do this thing, and we, this is the obvious incidence variety. I look at a polynomial, well, if you like, it's f. I mean, you can identify f and x here. F and some plane lambda, and such that f restricted to the plane lambda is equal to 0, right? So this is the idea. And this gave us a wonderful geometric understanding of what this variety f is, because then we could simply, just using this idea, we see that if and what we're interested in, of course, is the fiber of this thing. So we had the form that f k of xf is just the, so this we'll call pi 1 and pi 2, is just pi 1 inverse of this point f these are all the planes where f is 0. But of course, then in looking at the other side, we see that this is just equal to the 0 section on the Grassmannian. So instead of looking, which is sort of mentally seems reasonable when you look at this f, you just look at it right and try to calculate the planes on it. We look at this thing as a subset on the Grassmannian of planes that are in a particular variety. And that's fairly easy. So then this is just equal to the 0 set of gamma f equals 0, where this gamma is the following, is that you just have in this Grassmannian, oh, that's the same thing again, so G N, you have the usual topological bundle, and you just look at the sim. This is where we can get sim D of S star. And this gamma F is simply this formula here, is just gamma F is just equal to the restriction of F onto the corresponding S. Right, so if I take S, the plane corresponding to this thing, then I obtain, since F is a degree D polynomial, I'll have a degree D polynomial on S. A degree D polynomial on S is precisely an element of the symmetric product of S star. Okay, and so we represented it as a 0 section, so this is where our formula was. This time, this so then, in principle, we have a formula. We have this formula. Fk, the class of Fk of x. So then again, x now is a degree D hypersurface of degree D, which is just the top Chern class of this thing, and of course this has the rank is the same story as here. So it's this is the number of polynomials, except now they are in a k plus 1 variables, so k dimensional vector space. So the rank, so let's just write a few numbers out here now. So the rank of this sim, these are the polynomials on a S is a rank k1. and k plus 1 sim E of S star. So this is just, so the same thing as for N, but now it's K. Yes. And so that it just means that this is just the top term class. So the vanishing of a section of a vector bundle is just the top term class. So you put that little thing in here. So the other it's like this. Of this one. And this is, so we think of this now as lying in the Grassmannian, of course. So this is the final form that we get. Okay, so maybe another dimension calculation can just follows from this. Since we now we have all of the formulas. So the dimension of this phi capital, this space is just so how do we calculate? So we just take well, it's a subset here. So it's n plus the dimension of Grassmannian, I put it down with k plus 1 times n minus k. And then in each fiber, you have yes, so the fiber of an element here, so P2 inverse is precisely the space of, right, so when you take the product, so P2 inverse is the space of forms F, which vanish on lambda, so let me write it down also. So P2 inverse, let's write it here. Which is just the set of F's of forms which vanish on lambda. Well, so this is actually sort of is a tautological, some circular thing. But this is now simply a linear condition on F, right? So saying that a polynomial of degree D vanishes on some subspace of degree K just means that it's certain coefficients vanish. For example, you can assume that lambda is the first A coordinate. So in fact, it's precisely the restriction is just the coefficient here, which need to vanish. So we just need to subtract actually this number from this. So again, this is just the space of coefficients for a fixed set lambda, fixed plane lambda, of the set of all degree D polynomial in n variables, which should vanish on this. And so this is the condition of vanishing, simply a linear condition. This. Okay. And so now if I just so that I derive the expected dimension of this thing, which of course should be precisely that. So so of course the expected dimension, well, you can also calculate from here. There is this. Well, now I put it sort of in two different ways. So doing it this way now, I just look at this variety and I subtract n from it, right? Because it's a fiber F. Is a fiber of a map on Pn. So if I take a point and take an inverse image, an expected dimension is just I have to subtract n from this. So you're just going to go flat here. Okay. But you can also see it from here, of course, because it's you just look at the Grassmannian. In the Grassmannian, you look at the vector bundle of this rank, and of course, the zero section will be just the difference. Okay. So now I go to talk a little bit about what this means actually, because this is really great. But, so let's just, this was all just the setup, but let's just go back here. I mean, this is the key point. So we have this FPX, so maybe let's just do, before I go on to, let me just finish this. So let's look at some interesting situations. So this was the very general case of any lines in any, in any degree. So there's two parameters here. So there's the degree, well, the dimension of the total Pn, the degree of the hypersurface, and the dimension of the line of the one. So first of all, let's just look at the k=1 case. So that means just lines. This is what I was talking about. So how does the formula simplify then? Well, then it looks like then dim f expected dimension of f1 of x is just equal to k+1 is 2 times n minus 1. And here is just d+1, choose 1, so it's just d+1. So this is just 2n minus 2 minus 3 minus. Okay, so this is what we get. Okay, so obviously, I mean, the interesting thing about the thing is 0, because I'm being counted. And so interesting situation. So let's just discuss that. I mean, in principle, this actually is meaningful in any case, and we can calculate it, but you'll see already in this case it's not so easy. So an interesting situation when x dim equals 0, so what I mean is that the degree, so fx is equal to 2n minus 3. Okay, so for example, I mean, the first kind of interesting thing would be n equals 3, right? So n equals 3, so and d equals 3, 2, 3, and then n equals, say, 4 and d equals 5. I mean these are the interesting situation. That's when this is 0, the expected dimension is 0. So we are looking for lines in cubic hypersurfaces in P3, or we are looking on quintic hypersurfaces in P4, etc. So those are the numbers we need to calculate. Okay. So first, I think I didn't finish this last time, this calculation, so let's just quickly do this. So let's just do this case. Let's just calculate this first case. So this n equals 3. These things are, as you see, it's mathematic. It could be a little difficult side, but really not that hard. So we just need to calculate so in this case, we are looking at G2,4. So this is the Grassmannian of 2,4, right, which is G1. So remember that we have a complete description in this case of the ring. So in this case, remember it was just so 1 plus it was, so just a second. Okay, so let's say, should I use some lambdas? Yeah. Yeah, so
well, but it's just
yeah, so it's just the reason one needs to be just a little careful. Yeah, so let's just first write this out. Okay, there's just two languages, and you have to choose the language correctly and show this. So the point is we have this S, right, and the Chern classes of S is just 1 plus alpha plus, well, let's call it C1, C2, which is equal to 1 plus x1 times 1 plus x2. So these are the Chern roots, these x's, so the symmetric polynomial, so this, oh, it's a symmetric polynomial version, it's this one, and then the usual version is this one. And, well, in fact, there is a way to do it, just symmetric polynomials, but we already got used to this, so it makes it a little more difficult. So now, what I was trying to say here, why I stopped, is that, in fact, from this point of view, if you look at, so here we see that this is just A well, we're only interested in A forms. Well, let's do this first, sorry. So let's just see what we're actually trying to calculate. We're actually trying to calculate, well, actually, let me just start with that. Well, in this case, we'll not really change anything. Just simplify some certain signs that I need to worry about. And now D is equal to 3. So what we are trying to do is just to calculate sim 3 of S star. And so now this does not look so obvious, but here it's fairly clear, right? So if these x1s represent sort of, by the splitting principle, if you have this is now a rank 2 vector bundle. And this rank 2 vector bundle, so these x1 and x2 represent the 2 linear coordinates on it. Then in the to represent the cubic polynomials, you will, so maybe let me explain this a little bit here. So the idea is that we use the splitting principle. So what I mean is that suppose S is a rank 2 bundle, so it's just some direct sum of 2 lines. Well then, let's hold it this way. Let's just totally complete actually this S star. So then of course it's clear that if I look at the symmetric product, then the symmetric cube, so there's just then 2 linear coordinates on S, right? It's x1 and x2. You can think of x and x2 as 2 linear coordinates on this vector space. So then the sim 3 of S on S star is just going to be cubic polynomials on this 2-dimensional vector space, and those are, so there's an x1 cubed, x was not such a good way of saying it, sorry. X1 cubed, x1 squared, x2, x1, x2 squared, and x2 cubed. These are the 3, they form a base. So the idea is that if you split this bundle in 2, then this bundle will also split in 4. It's a 4-dimensional bundle, but the 4 line bundles that are easy to express with this. So this is just going to be, just following this, just going to be L1. This is really a terrible thing that I did now. Apologize. But these x's have nothing to do with that, so. Yeah, now I know why I wrote lump originally in my notes, but for some reason I didn't like the idea of, yeah, so let's go on by, so. Sorry. Okay, so corresponding to these two things, so this corresponds here to y1 and this corresponds to y2 as linear coordinates, and so then you just y1 cube, of course, forms a section of the bundle L1 cubed. Then you have L1 squared. Sorry, I wrote it that way. L1 L2 squared. L1. So this means tensor product when I multiply line bundles. L1 squared L2. L2. Okay, so this one is simply, if you assume that this is a direct sum, then this is also a direct sum. evident because if this direct sum has this basis, then this symmetric product, the polynomials have these bases. And so that, of course, allows us immediately to write down, you simply, is going to be a direct sum of line bundles. So the total Chern class is just going to be a product of the total Chern classes of these line bundles. And of course, then you take a cube of a line bundle that just multiplies its class by 3. So it's just going to be the product of the following things. So the first is just corresponding to L1 cube is just going to be 1 plus dx1. The next one is just going to be 1 plus, and then you just look at x1, x2 squared, 1 plus 2x2. So the Chern class is added when you take tensor products of line bundles, as you know. And then you have so this is the main calculation actually. So we have this, so we can multiply this, but we're only interested in the top part, in actually C4, right? Because we are interested in k plus d choose k. That allow me to continue here. We are interested in C k plus d choose k of this bundle. So C k plus d choose k. So k is 1 and d is 3, so that's just C4 of this bundle sim 3 as dual is just, so that's going to be the top Chern class, so that's just the product of these things, right? So that's the top, the C4. So there's just the 3x1 times 3x2 times x1 plus 2x2 plus x1, 2x1 plus x2. Okay. So here we are, just here. Anything so far? Yeah. And so, I guess I'll just finish here. Oh, that's not such good. We've got another space and it's not all over the place. Okay. Yeah, I apologize, but I'll just use this space notation. Okay, and so now the problem is, going back here, is that this thing we actually had described, I only interested in A4 really. So remember that in A4 we had an equality. So A4 is just one-dimensional, and we had the following equality that C2 squared, that was the basis element. And then we had, then we have a basis element which is C1 squared, C2, and then there was C1 plus 1. These are the four possible things. And actually have the following statement that the degree, so the relation are as follows. So C2 squared twice C2 squared was equal to twice C1 squared. C2 was equal to C1 to the fourth. This was the actual formula. And of course, the degree of C2 squared is equal to 1. So the degree of C2 squared is 1. The degree of C1 squared of C2 is 1. And the degree of C1 to the fourth is 2. This was 2. There are 2 lines intersecting 4 lines. And 4 fixed lines in 3-dimensional space. Okay, so this is the calculus, and I need to now convert this thing to this thing. So when you do that, you just, so I can write this out now. So I write this here, degree of C2 squared is 1. Okay, and so now let's just continue this thing. So what I need to do is just, the degrees of these I know very well. I just need to rewrite that thing. So first I just have 3x1 x2, that of course is just C2. So this is just equal to 9 C2. And then I just have that other thing, and so, well, there's a number of ways of doing it. I mean, you can you can write, well, you can just write it out. Maybe that's the simplest for now. So it's, yeah. Or you can do something more clever. Well, that's right, more clever. So more clever is like this, you do C1. So the first one is C1 plus X2, and the second is X1 plus C1, right? So this thing would be just 9 C2 times, so I multiply through, so I get X1 plus X2 times C1, which is just C1 again, so it's just C1 times C1, and plus C1 squared, plus X1, X2, plus C2. So this is what I get. Right, so again, the idea is that C1 is X plus 1 X plus X2. So I just take C1 times X1 plus C1 plus X2. That's X1 plus X2 is C1. That's one thing. And another thing is that I just have C1 times C1. That's also C1 squared. And plus the last term X1 times X2, that's C2. Just it's a little side by side. And so anyway. So finally, this is what we get. And then we see very well that what we have is here we have C1, C2 times C1 squared, so that's the degree of that is 1. C2 times C1 squared again, and then C2 times C2, the degree of that is also 1. So all of these here, this part where the degree is 1, you don't get C1 to the 4. So actually each of these just contributes 1 to this, so this is just going to be 9 times, so as many terms you see here, so there's 3 terms, so that gives you 27. Okay, so again, C2, so for example, one term, 9 times C2 times C1 squared. C2 times C1 squared, the degree is 1, so that just gives you a 9. Then you have the same thing again, and the last one, 9 times C2 times C2. C2 times C2 is degree is 1, so this goes to 1. So all 3 terms here just give you 1. So 9 times 3 is 27. That's the answer. Okay. Okay. So then I stop. Now I think that way over probably. And then well, the question now. That's wonderful. We calculated this, but of course, this is now. Well, remember, I mean, the Chern class represents that set. So this is now this finite set of 27 points. So that's there are 27 lines. Only if this section that we're talking about here, right, this came from here, is gamma f equals 0, we are calculating its class. But only if it's transversal. If it's not transversal, then it could be anything. It could be higher dimension, it could be lots of different things. So the next technical thing, which this you can do anytime, but this other next technical thing only works, we only know how to do this in lower dimensions, is to verify that there really are 27 lines. The theorem is, in this case, is proved it's true if you take a generic, smooth degree 3 hypersymmetry set in 27 lines. Okay, so that's, but this has not been proven. Okay, so that's the thing.
So what does this give us? Finally, our calculation. So let me finish. So we're here. So I ended. So just finish here. Tells us that conclusion, if this section gamma f, so we are still, remember we are in this setup, so we have, but now a concrete one, so we have n equals now 3 and d equals 3, and so we are in this whole setup, and finally we are calculating gamma f, where we are taking a section of this bundle, Sim3 of the tautological bundle, and we obviously set theoretically, this is precisely true. The 0 set of this section is precisely those lines in the Grassmann which line that particular variety xf that we have. The variety where f vanishes. Of course, for enumerative geometry, what we'd like to know is really how many they are, because I mean that how often this theoretical number that we calculate, is 27, is actually the correct one. And so for that, of course, we know we have a definition from our definition of Chern classes. We remember that if you have, if you know the Chern class, so for example, in this case, it's a top one, if you, in order for truly to be true that this variety's class is equal to this one, so that this is really an equality, so this was just a sort of a calculation, well, so I should put this in inverted commas maybe. So if gamma f is, well, generically transversal, but this is not important now because we only have points. Transversal as a section, as a map from G to sim D, then indeed, then Fk is equal to this C of this sim thing, so that equality it really holds. And in particular, in our case, this means that in that case, we can make the conclusion about the 27 lines. But in reality, the theorem, so I apologize, so here I was a little bit rushed. I wrote that this is true, but actually this is only true, of course, under the condition that the section is transversal. Otherwise, of course, it's not true. The section could be 0, and then you have the whole of Grassmannian. Okay, so this is only true in this transversal situation. But the theorem says that in this case, that if, so we are in this setup now, n equals 3, so n equals 3, d equals 3. Still in this setup, any smooth cubic surface has exactly 27 distinct lines. On it, okay? So in fact, for our current example, this is true. So if this space, so the only condition we have is that this surface is smooth, but that's kind of obviously, well, we'll see, is necessary. But this is quite remarkable. I mean, in general, this would be difficult to show. Okay, so let's, so I just don't want to erase this, that's why I was running around this. It's two boards there. So just, so now we need to prove this, right? So this is not obvious from what I did now. This is not clear, but it's true. So just first, of course, I mentioned this before, just some remarks first, is that, of course, if the space, if the cubic is not smooth, for example, it's not reduced, then, of course, this is definitely not true. For example, if I just take f equals, say, y1 cube, this is a cubic, but clearly the set of lines that are xf will contain P1 of some sort, right? P1 where, say, y2, y, so, where y1 equals 0, or something like that. Or maybe in a P, it's a P2 maybe even. Sorry, P2. Right, so, yeah, that's what I want to say, because we're looking at lines. So, no, sorry, so what am I saying? No, this is correct. Sorry. So then actually in this case is XF is P2, but a thick P2, right? I mean it's a non-reduced P2. It's a triple P2, but it contains a P2, and so the number of lines is not 27. The number of lines is infinite now. Okay, so this is So now this f1x in this case is, well, as a scheme, it doesn't matter. But the point is, it's infinite. So it's certainly not 27. So that doesn't work now, right? So, of course, in this case, this is not smooth because it's not reduced. This is this non-reduced thing that we were talking about at some point. Okay. So how to do this? So there is now a clever trick that we are going to use. So you see, the idea is that there is sort of three things that are more or less equivalent. So this I'm not going to prove precisely, but I would like you to understand what the trick is. So the idea is the following, is that, so let me just come back to this picture because this is really the important thing. Right, so we have this incidence variety. Remember, the amazing fact was that why this was so great is because this was a smooth, this is just a projective bundle over the Grassmannian, so this was a smooth codimension, their calculated variety. Okay? So now the point was that in order to calculate the phi, which what we are interested in, so there's this calculation of, so I have to actually come back and write it down again, sorry. So this is pi 1, this is pi 2, and this was this bundle S star. And so the idea was that f k of xf was the same thing as pi inverse of f, pi 1 inverse of f, and this was the same thing as the set gamma f equals 0, where gamma f is the section into on the Grassmannian of sim ds star. Okay, so this is our setup. So the point is that we have a triple view of the thing. This is what's important. We have the same space in sort of three different ways. This is just the set of k-planes in xf. It's a pullback, it's an inverse image of a point here. And it's at the same time, it's a zero section of a bundle here. And this is all the same thing. And so this is what we will use now. So obviously, well, of course, it's a little fishy what I'm doing in the sense that, for example, this I only defined as a set. So then here, you can, if you have a zero section of a bundle, that you can give a scheme structure to that. And an inverse image, you can also give a scheme structure. So, for example, you need to prove that these two scheme structures are the same. So there is some things to do. I mean, this is a little bit fishy, but that's not so important. It is the same, so it does work. What is important now, as we calculated, so in our setup, obviously we are precisely interested in the following thing. So is gamma f transversal? Because if it is transversal, then this equality is true, and then we are all set. And gamma f is transversal. Well, it's easy to see. Well, of course, when the thing is transversal, then this is equivalent to saying that this fk, xf, is smooth. It's the same thing. So this is sort of the implicit theorem in algebraic geometry. So if you have a transversal section, then, or generically transversal, but now since we only have points, now this just means that those points are smooth that we're calculating. And so that's basically the implicit function theorem. But now, if we think of it that way, then you see, to say that that thing is smooth is equivalent. What we need to try to calculate is remember, the definition of smooth, that we need to calculate the tangent bundle of this. And this is smooth, of course, if the dimension of the tangent bundle of fk, xf, is equal to the sorry, so what am I trying to say? Yeah, but what I mean to say is that I look at a particular element L now, so for every L in fk, I want that I look at that tangent bundle that we're calculating tangent bundle of L f at k, and this dimension should be the expected dimension of fk. Right? Because that was a definition of smoothness. The definition of smoothness is that there's sort of an expected dimension of the variety. Now it's 0, so it's really easy. And you want that the actual tangent bundle of L at that point has the same dimension of this. In our case, it's 0. Okay? And now this brings us to trying to understand, so what does this really mean? But now we can think of this as something happening just on the surface. I mean, what we are asking is that I have I'll say a line on a cubic, and I'm trying to deform it. I'm trying to find what the tangent bundle of that is. And so this is now a change of philosophy, right? Here we were talking about transversality of some section on the Grassmannian, and now I'm converting this to trying to deform the line inside the surface. And so this now, of course, in our case is equal to 0. This is what we calculated. That's the whole point. And I have to talk about this a little bit. And so this I'm not going to justify completely, but intuitively this is completely clear. So this is a theorem definition, if you like, is that this TL, so again, we have an L, element of Fk, but I think of L, of course, so L is also a subset in XF, right? So it's just a line on the cubic surface, we think of. So TL Fkx is just equal to the normal bundle of L in X. I'll denote this by this, so this is the normal bundle. Bundle, I recall that the normal bundle was just this thing fit into this sequence, so I have a line, and then I take the tangent bundle of the cubic surface. Of course, I think of it as restricted on L, and then the quotient, this is an embedding, and then the quotient is this, if the subsets are smooth. This is the definition of this. Okay. So
maybe global sections of this of the normal bundle.
Ah, sorry. Yes. Yeah. Sorry. Yeah. Thank you. Yeah. Sorry. Yeah. And so I will not justify this, but it's quite logical that if there is even an infinitesimal deformation of some sort, so if this thing is not smooth, in our case, so somehow there is a direction in which at least even infinitesimally you can deform the curve, then its normal bundle will have sections. It's precisely you have the curve, and then this is the normal bundle, and there is a sort of if you have a one-parameter family, then there's clearly a section, and this is even true infinitesimally. Anyway, so we accept this, if you like, as a theorem definition. So we'll just say that so a corollary, which is now so this is actually not quite interpretable in our setup because I didn't truly define what this tangent bundle is. So, well, if you work it through, you can actually find a definition. But for us, I just wanted to show you the technical corollary way of actually getting this proved is the following, that if, so this is true in much great generality actually, but just in our case, this gamma f is transversal at some L in X, or, well, no, so sorry, L in the Grassmannian. So you see, this is the if and only if this H0 n Lx is equal to 0. Okay? So this is finally, so there's some technical things that you have to go through here, and as more or less informally this is clear, you calculate this. Well, what is least clear is this thing. So you can define, there is a scheme structure on this Fk, so using that scheme structure and the definition of the Zariski tangent space, you can define the tangent bundle. Smoothness was defined this way, and so this actually you can sort of define. This then makes sense to say that this in this case, this Fk is smooth, and then you have to believe in what I said is that the transversality of this section is equivalent to the smoothness of the zero part of it, and then that in turn is the smoothness of the zero section is precisely the equality of these two things, and then if you believe in this thing, then that precisely is equivalent to this condition. Okay, so that's the logic. So I didn't prove every detail here, but the corollary actually completely makes sense in what I said. This is not completely well defined, but the corollary is certainly completely well defined in our universe of understanding of what's going on. Okay, so and then now again we arrive at a beautiful little calculation that we need to prove this statement. We need to prove that H0 Lx is 0. So this is, but remember what is L? L is a line in P1, so it should be a relatively easy calculation. So NLX is simply a line bundle, right? Just so what we're talking about over P1. Okay, this is what we're trying to calculate, right? Because L is a line, so it's P1. Right? This is the line bundle. It's a line bundle over L, but L is a P1. And because of the dimensions, we are in n equals 3. We are looking at XF, which is a hypersurface, so it has 2 dimensions. And you have in this 2-dimensional thing, you have lines, which are 1-dimensional. So the normal bundle is 1-dimensional, right? So you have P3, 3-dimension. Here you have XF in it, which is 2-dimension. And in XF, you have a line like that, and that's L, which is 1-dimensional. So the normal bundle is a line bundle. It's 1-dimensional, rank 1. And so what this is, in this case, and this is why in this case this can be done easily. Actually, in the general case, this is not even true anymore. So if you go to the, this will not be true for the next case when you have d equals 5 in n equals 4. So this is only really works in this case because now we are just calculating H0s of line bundles over P1, and those are really easy to do. Okay, so in fact, the line bundle over P1 is always L is no, this is really a terrible notation, sorry. So line bundle E over P1 is just E is, well, if you think of sheaves, so it just has a degree O of D of, let's call it M. Right? So the point is that the reason this is easy because we can easily classify all line bundles over P1. They are just O of M for some M in integers. So this M is that we need to, and H0 is equal to H0 of E in this case, or O of M equals to 0 if and only if M is negative. right? So O of 0 is just a constant, the trivial bundle. It has a single section, the trivial section, and then of course, if you go higher one, in general, H0 of O of M is actually equal to simply, is equal to just the degree, well, let's denote it this way, R sub M, say, where R is just the polynomial ring in the two variables y1 and y2. Is the ring, and Rm is the degree m polynomials. Okay, so just here what I'm doing is, so this is true, and I'm just describing, well, in case m is positive, so that's not the case, then I can actually completely describe actually what the sections are. It's just I look at this two-dimensional vector space projectivization, which is P1, and then say its coordinates are y and y2, and then of course the sections were these. I mean, this you know very well. Okay. So to prove this thing, this 0, I need to just calculate this integer m. That's the point. And that basically calculating, you can do it calculating Chern classes. We can do again, use our Chern calculus. So I will write down first a general, actually I don't know, do we need this now? Just a sec. Maybe this time. Let me think for a second. Let me just give this sort of this general thing because it might be useful. Now we don't really need it in full generality, but theorem about normal bundle or properties of normal bundles. I mean, this is partly trivial, partly simply a definition that I'm going to tell you now. So, yeah. So one thing is that this is the definition in this when Alex. Well, let me write it down again. So if y, x, everything is smooth. So this is the first thing, then this is a definition. Then we have this ty, tx, and yx thing. Exact sequence of bundles, and this is the definition, nyx. So then one little property here is that what I can do is that I can write it down the following way, that, and the sheaf theoretic sense. So I'm sorry, but I identify sheaves now with bundles. So what I mean is, well, you can look at it this way, it doesn't matter. You do hom over y, and then you construct the following bundle. You look at the ideal sheaf. So I will talk about this a bit more later, so you can ignore this for now if it's not clear. Just the dual. So the conormal bundle, if you like, so this actually just says, is precisely this bundle. You look at the ideal sheaf divided by the square. Okay? So I'll explain this a little later. This is now, we are not going to use that, but I want to put it here, because it's a little useful. This you can also think of as another definition if the thing is not smooth. Okay? So, because this thing is completely meaningful. Even ideal sheaf exists for non-smooth varieties as well. So one use of this is that you can understand this also when it's not smooth, and I wanted you to understand that this can be done. And then the other thing is an almost obvious statement, which is that if you have three things, then of course you have a similar, so it's a generalization of the definition, if you like, from point, so it goes yx restricted to y, right? So, well, in the smooth case, this is true. This is definitely true, so let's go on smooth. And this is what we are actually going to use. And maybe one other important thing is a generalization of something you had as an exercise, but is what's called the complete intersection thing, which here, where I can actually define n now using this in greater generality, is the following thing, is that if you have some bundle E x, and you have a transversal, generically transversal section gamma, and y is equal to gamma 0, this is what we call a complete intersection, by the way. So this is the complete intersection case. So a complete intersection is this setup when you have a vector bundle and a smooth, say smooth variety, and a transversal section. So in this, you define the y as a 0 section, then n y x is simply equal to e restricted to y. Okay, so this is a simple theorem that you actually checked in the line bundle case, and so this is also true in general. So these are sort of the basic things that we need. Okay. So, yeah, so but of course now, because we have a complete classification, I mean, this is what's really helpful, this statement, which is not true in higher codimensions. We have a complete classification of line bundles and projective spaces. To identify the thing, it's enough to calculate just the Chern, the Chern classes of this bundle, right? So the Chern class of OM. So now to identify these things, maybe I'll still write a little bit here. Just remind you that the Chern class, say the total Chern class of O of M on projective space is just equal to 1 plus M times Xi, right? So well, Xi is just the point. I mean, this is really just on P1. This is much easier than 4. So we just need some, using this thing, need to make some simple calculation. So let's use this property here. So we precisely have 3 nested varieties, as I showed here, right? So in that, now we have y, which is equal to our line L. You have x, which is our xf. And we have W, which is just the whole of P3, right? So this is our setup. And let's now use this thing. So what is, we are trying to calculate NYX actually, right? That's Y is L. So if we understand these two, then we are doing very well. And so we have 0 NYX. So here we put NYW, okay? But so NYW is really a very simple thing in this case because it's simply the normal bundle of a line in P3. So this is just the normal bundle of P1 in P3. And here, this is also very easy because X W according to this, so X is of course a cubic surface. So it's a 0 section of, so here x is just equal to mu equals 0, where mu is just a section of O3, right? That's what it means to be a cubic surface. So for that reason, it's just here n is equal to just O3 restricted to y, which is just O3. Restricted to L, on P1. So this is easy, and this is also easy, so this is a little exercise. So basically, this comes because we know, well, you can use the same thing if you like. I mean, you know, P1 is a complete intersection in P3, and you need just 2 linear conditions. So P1 in P3 is, sorry, so to calculate this, you simply recognize that P1 is just equal to some nu 1 and nu 2 equals 0, when these nu I are just linear functions, so they are just sections of O1 on P3. So this is just O1 plus O1. So finally, the calculation looks like this. So this is just O1 plus O1, so we arrive at this thing. So it's a rank 2 bundle, 2 line bundles, and this is the extension. That's what we got. Okay, and so now it's really easy because you just calculate the first Chern classes are actually additive. So we know that C1 of n Lx is just equal to C1 of O3 minus C1 of O1 plus O1. And this is, of course, sorry, the other way around. Because the sum of these two is this. So this is this minus this, right? So it's C1 of O1, sorry, O1 minus the C1 of O3. And this is, of course, 2 when you calculate it, so you get minus 1. Okay? Times psi, I mean. It doesn't matter. So the degree is minus 1, and this is precisely means that and this is what we wanted. So this is pretty amazing. So you see, somehow, first it seemed like we were not doing anything because, okay, so we represented this 27, with this cycle of 27, some zero section of something, but actually we amazingly just using some almost nothing, just calculating, doing enumerative geometry, just because all this is enumerative. These Chern class things, all these things are just enumerative, using an absolutely minimal non-enumerative thing like proving that a negative degree bundle has no sections. We actually proved that there are actually 27 different lines. Okay, so this actually is 27 different lines. It's just pretty amazing. Now, I just want to point out one thing, which is that this does not work already in the next case. So this does not work for the other cases. So for n equals, what was it, 4 and d equals 5, right? Yeah, that's the next one. 3, 3, 4, 5, yes. So why doesn't it work? So if you can start this cycle. So we represent this f as a zero section of something. We calculate the thing. So we can calculate this thing. So we can start the same thing. So we have f now is still 1 of xf, which is still c of, I forget now, what is it? The next one is c, oh, no, I didn't read it. So something of that bundle, sim of d is 5 of s this, and so you get, yes, it's k plus d, choose d anyway. So it's the same, exact same formula. So I wrote down, it's d plus 1 actually, so it should be 6, I suppose, right? Anyway, so you calculate this, and so you find that this is equal to I think 2875. Okay, so there's a calculus similar to the 27. It's just a little more difficult, but actually I think I can still do it by hand, so you should be able to do it too. So this is easy. So that part, there's absolutely nothing wrong with it, and then the logic is exactly the same. It still works. You can still argue that if you calculate, so there was nothing wrong with anything I did there, that if H0 is 0, then these points are separate, the transversal, all that logic works. So where the thing dies is the following little problem, is that now, you see this is hypersurfaces. So when you arrive here, then the problem is that the dimensions are now not quite so great. So here, where am I? Which part do I understand? TW. This is still okay because it's a hypersurface. This was the X normal bundle of X in P3, so this is still a line bundle. This is still okay. But now, of course, the codimension here is 2. Right? So this is because the line, you are in 4-dimensional space, so the hypersurface is 3-dimensional, but the line remains a line, so you have a 2 dimensions to this. So the rank, here I should write here. So the point is that the rank of y of n yx is equal to 2, right? So the codimension is 2. And now the problem is that if you have rank 2 bundles, even on P1, you can still calculate the Chern classes. That it still works. But just because you know the Chern classes of a bundle, you don't necessarily know whether it has sections or not. The first Chern class, say, of the bundle. Because it could be a very positive, some a very positive, and a very negative one, for example. So actually the theorem only true then for a generic smooth surface is not true for a special kind. And so I need to stop here. So what we are going to do next is the following thing. So I will introduce what a Hilbert scheme is next time. So the question is, suppose I want to not move just lines, but I want to find more general things. Like I want to find curves or some other things on surfaces, and I want to describe count them in a similar way. So then the problem is that this thing is still going to be okay. So we still have this phi, and it's still here maybe this p. So we need to replace this in some way. So we need to replace this triangle by some other things for when the subvariety, when counting subvariety of other than lines and linear degree 1 things. And this will be more difficult, and so I'll have to also explain the Riemann-Roch theorem next time, and a Grothendieck theorem, no, just the Hirzebruch-Riemann-Roch theorem, and various other things which are necessary for this. But so I will not prove everything, but anyway. Okay, I'll stop here.